All right. Good morning, everybody. Today we will have 30 minutes of lecture, and then after that, we will do the in-class assignment number 8, which is the last one for this semester. Okay, so remember that we are now talking about covalent compounds and how to draw the Lewis structure of covalent compounds. You can always use the Clark's rule to help you uh, to figure out what's the structure of the compound. And the last thing I showed you on Tuesday was how to calculate the formal charge. Calculating the formal charge will help us to decide which structure is the most probable for a covalent compound when more than one option is possible. So let's pick up where we left. So I introduced you how to calculate the formal charge of an element. We are always going to use the number of valence electrons minus half of the bonding electrons minus the non-bonding electrons. Remember, each covalent bond uses 2 electrons, okay? And we did an example for the PCl3, and then we moved on for the case of the sulfate. In the case of the sulfate ion, we may have several possibilities for the covalent structure. Using the formal charge will help us to decide which structure contributes the most to the sulfate, or which one is the most stable. So we also draw all the possibilities, and they are here. So I draw 4 possibilities. All of them are possible, but there is one structure that is the most probable to happen. So let's calculate the formal charge for all the atoms in all the 4 possibilities, and that will help us to decide which one is the one that contributes the most. Which structure is the one that is the most probable to exist. So let's start here on the left side. So the first structure has sulfur making 4 covalent bonds. All of them are single bonds with the 4 oxygens. So I'm going to start calculating the formal charge for the single bonded oxygen. So I'm going to represent this way, Fc, between parentheses, a single bonding oxygen. The formal charge is going to be equals to the number of valence electrons for this element, which is 6, minus half of the bonding electrons. There is only one single bond, therefore we have 2 bonding electrons for the oxygen, minus the number of non-bonding electrons. Okay, 2, 4, and 6. Therefore, the formal charge for the oxygen connected to the sulfur through a single bond is going to be 1 minus. And I'm going to write this way, in between parentheses on the top right corner of the element. All the other 3 oxygens are connected the same way, therefore the formal charges are the same. Okay, so all the 4 oxygens have formal charge 1 minus. Now let's calculate the formal charge for the sulfur. Going to represent Fc between parentheses S. Same thing. Number of valence electrons, which is 6. Sulfur is in the same group as the oxygen, minus half of the bonding electrons. Now pay attention that for sulfur, we have 4 single bonds. Each single bond uses 2 electrons. Therefore, we have a total of 8 bonding electrons, minus the number of non-bonding electrons for sulfur is 0. And that will give us a formal charge equals to 2 plus. Let's represent here 2 plus. Okay, so ideally, the formal charges of all the elements in the structure must be 0. Okay, double and triple charges are not stable. Therefore, for the first structure, for the first possibility of sulfate, we have here a double charge localized at the sulfur. Therefore, this structure has low probability to happen, okay? Because of the double charge localized at the sulfur atom, the first structure has low probability to exist. So now let's move on to the second possibility and let's do the same thing. So let's figure out the formal charges in every atom and let's then analyze. So notice here that we have 3 oxygens connected to the sulfur through a single bond. So that's the same case as the first case. So we don't have to recalculate the formal charge for the oxygen connected to the single bond. It's always going to be 1 minus, okay? So that saves some time. Always when oxygen is connected to another element through a single bond, the formal charge is going to be 1 minus. Now we have here a second kind of oxygen, which is connected through a double bond to the sulfur atom. For this oxygen, we have to calculate the formal charge. So formal charge for the oxygen connected through a double bond is going to be equals to 6 minus half of the bonding electrons. Attention now, because now we have a double bond, therefore we have 4 bonding electrons, okay? Minus the number of non-bonding electrons. We have here 2 and 4. That gives us a formal charge equals to 0. Okay, so oxygen connected through a double bond has a formal charge equals to 0. And now let's calculate the formal charge for the sulfur. Same thing, 6 minus half of the bonding electrons. Now we have here sulfur making 1, 2, 3, 4, and 5 covalent bonds, therefore 10 bonding electrons. Okay, so remember that each covalent bond needs 2 electrons, and sulfur does not have any non-bonding electrons. Therefore, in this case, the formal charge for the sulfur is going to be 1 plus. Okay, so making the double bond, we decreased the formal charge of the sulfur from 2 plus to 1 plus. Therefore, the second structure has a higher probability to exist. Let's analyze the third possibility and see if the third possibility will give us the higher number of zero formal charges, and then we make a decision regarding which structure is the most probable. For the third possibility, now we have sulfur making two single bonds and two double bonds. We know that always when oxygen is connected through a single bond, the formal charge is 1 minus. So we will have 1 minus on the oxygens on the left and 1 minus on the oxygen on the right. Oxygen making a double bond will have formal charge equals to 0. So therefore 0 on top and 0 at the bottom. Now what's left is to calculate the formal charge for the central atom, which is sulfur. Formal charge for the sulfur is going to be equals to the number of valence electrons, 6, minus half of the bonding electrons. So let's count how many bonds sulfur is making. 1, 2, 3, 4, 5, and 6. Each bond requires 2 electrons, therefore we have here 12 minus 0 because there is no non-bonding pairs. So that will give us a formal charge for sulfur equals to 0. Okay. If we compare the second structure with the third structure, we see that the third possibility, the third structure, has the highest number of zeros. So that's A plus. However, we have a negative charge localized at the oxygens. Every time we have a negative charge, it has to be located at the most electronegative atom of the bond. Okay, so oxygen is almost at the top of the electronegativity order, while sulfur is almost at the end. So it makes sense that oxygen has a negative charge when bonded to sulfur because this atom can attract towards closer to it the electron in the covalent bond, okay? So although it's not 0 for everybody, it makes sense that the formal charge of the oxygen is 1 minus. And another detail here, the sum of the formal charges of all the atoms in the structure has to match the net ionic charge of the compound. 1 minus with 1 minus will give us a net charge of 2 minus. So the third structure so far is the best. So let's see if the fourth structure is better. Okay, for the fourth structure, we have 3 double bonds and 1 single bond. Oops. So every time we have oxygen making a single bond, this will give us formal charge 1 minus. And in the case of double bonds, that will give us a formal charge equals to 0. Now let's do the formal charge for the sulfur, the central atom here. It's going to be 6 minus half of the number of bonding electrons. Now we have 7 covalent bonds, therefore we have 14 bonding electrons and non-bonding electrons. That gives us a formal charge for the sulfur equals to 1 minus. So adding an extra double bond compared to the third structure now put a formal charge of 1 minus at the sulfur. The sum of the formal charges are still 2 minus. However, now we have a negative charge at the least electronegative atom in the chemical bond. So therefore, this will not be a stable structure. So therefore, the fourth structure has low probability to happen because we have a negative charge at the sulfur, which is the least electronegative atom in the chemical bond. The first structure has a double charge, which also has low probability to happen. The third structure has the highest number of zero formal charges, and the negative charges are located at the most electronegative atom in the chemical bond. Therefore, the third structure is the most probable to happen. The second structure is not so bad. However, the probability is low. Okay, it does exist, but in a small percentage compared with the third one. Therefore, using the formal charges, we can decide which of the possibilities is the best. Okay, which form will have a higher contribution for the structure of the compound. And in this case is the third option because it has the highest number of zero formal charges and the negative charges are located at the most electronegative atom. Therefore, the structure of the sulfate ion has two double bonds and two single bonds. And in this case, we have a hypervalence for the sulfur. And that's how you use formal charges to decide which structure is the best. Okay, so now let's analyze one more thing regarding the sulfate ion. And with that, I would like to introduce the concept of resonance. So when you draw the structure of the sulfate, you have two double bonds and two single bonds. So there are two ways to draw uh, the structure of this ion. The first one is having the two double bonds in the vertical position, and the second one is to have the two double bonds in the horizontal position, which is the most correct form. The two double bonds in the vertical or the two double bonds in the horizontal. How can we decide which structure is the best? So one thing we can do is to crystallize the sulfate and do an X-ray diffraction of the single crystal And with that, we can have the structure of the compound. Okay, we can have the exact location of each atom. And with that, we can measure the distance between oxygen and sulfur and oxygen and sulfur. When we have a double bond, is expected a shorter distance. Okay, so the distance for a double bond is going to be always shorter than a distance for a single bond. So when we do the diffraction, we expect to have two bonds short and two bonds that are longer. However, when we look at the experimental data, we find a distance sulfur oxygen that's neither equivalent to a double bond or a single bond, but an intermediate between double and single bond. And most importantly, the distance between sulfur and oxygen is the same for all the four atoms, which means all the four bonds between sulfur and oxygen are equivalent. And the reason for that is that the double bond is not located in a specific axis, but it's moving around the compound all the time. Okay, so therefore, both drawings are correct because the double bond is not static. It is changing all the time. And that's the resonance concept, okay? So resonance means that the bond, the double bond, is not located in a specific bond, but it's moving around the compound. Every time we have a double bond next to a single bond, you usually have resonance. And to indicate resonance, we draw a double arrow here. So that means this bond is moving all the time, which makes all the chemical bonds to be equivalent. And the distance will be an intermediate between a double bond and a single bond. Okay, and that's the same case for ozone. Ozone has this structure, double bond on the left side and single bond on the right side. However, this double bond may move to the right side and form this compound. Because of the movement of the double bond, we call this structure resonance structures. Okay. And to indicate the resonance, we have the line with the double arrow head. Okay, to finish up here, so let's talk about uh, chemical bonds and bond distance and bond strength. So we have here an energy diagram as a function of the distance and two atoms. At the beginning, the two atoms are far apart, so we may consider them isolated. Therefore, there is no interaction between the two atoms, and we have a point of energy equals to 0. As the two atoms start to approach, there will be attraction, okay? They want to make a bond here. So there is attraction between the nucleus and the electrons that will start to decrease energy until they get to a point that this energy reaches a minimum. And that's the sweet spot, the ideal atomic positions. There is the max attraction, everybody's happy. At the lowest point, the distance between the two atoms are defined as the chemical bond distance, and the energy is the energy of this bond. However, if they get closer from this point, if they start to get closer, now there is a repulsion between the two nucleus because they start to get close to each other, positive and positive, they start to repel, and that results in an increase of the energy and destabilization of the compound. Okay? Always remember that the distance between the atoms at the lowest energy point is called bond distance. And the energy reached is the bond energy. So bond lengths and bond energies are tabled. So we don't need to memorize things. We need to understand why the bond length decreases, for example, as you move on from a single bond, double bond, and a triple bond. So now from single to triple bond, we are having more ties between the atoms, resulting in a decrease of the length, and that makes the bond stronger. Okay, so there is more energy when carbons are connected through a triple bond compared with a single bond. Okay? So very high energy for triple bonds, so this bond is pretty stable. And we can compare here as well a bond between hydrogen and fluorine and hydrogen and chlorine. So there is an increase in the distance going from fluorine to chlorine, resulting in a decrease of the energy. Okay, so atoms further apart, that's not a strong bond. Okay, and to finish up really quick here, let me talk about radicals. Radicals are any compound with an odd number of electrons. Classic example here is the NO, which has 11 electrons. So 11 electrons will result in an unpaired electron. Unpaired electrons are very unstable and they will look for another electron. Okay, they will capture electrons from everything that's around, and radicals are very reactive and they will oxidize compounds that are nearby. Okay, so with that, I think that's a good point for us to stop. So with that, we finished this chapter, and next week we will move on to the next one. So I will make the in-class assignment available on Canvas, so you can download all the questions on the assignments page, and I will be here available if you have any questions. Okay. So with that, have a good weekend, and I will see you next week.